Can you see the whiteboard? Hello. Hello. Can you see the whiteboard? Can you hear me?
Yes, sir.
Yes, sir.
Okay. So today we will start talking about logistic regression. And we will see how we can build up the hypothesis representation and decision boundary for classification. Okay. So in the last class we have talked about linear regression. So in linear regression we predict an output value which is found to be close to the actual value. Okay. So what we have what regression model we have used? So we have used a straight line equation. So that straight line equation gives us the predicted value which is found to be close to the actual value with the help of model parameters m and c. Okay. Now let us consider a few problems where we need to separate one sample from another sample, or one pattern from another pattern, or one condition from another condition. Okay. So let us consider the first problem. Biometrics authentication. Biometrics authentication. So in biometrics authentication problem, we will find we will try to find an answer that whether the person can be authenticated by the system successfully or not. If the person is authenticated successfully, then that person will be called the genuine person. Okay. Otherwise we will call the person is imposter. Okay. Genuine or imposter. So we can infer this decision either by yes or no, or 1 or 0. Okay. Now if we consider the second problem, whether a mail is spam or not, spam or not spam, then we can also infer this decision by yes or no. Okay. Or if we consider whether a tumor is malignant or benign. Malignant or benign. Okay. So we can also infer this decision by yes or no, or some numerical value like 1 or 0. Okay. So that means we need to we need to assign some labels to the predicted output. Okay, so in biometrics authentication, if the individual is found to be genuine by the system, by the biometric system, then we can infer this decision as yes or some with some numerical value 1. Okay, if the person or individual is found to be imposter by the biometric system, then we can infer the decision as no or some numerical value 0. Similarly, we can have the decisions for whether a mail is found to be spam or not, or whether a tumor is found to be malignant or benign. Okay, so for these decisions we can have some labels. Okay, so either we can have yes or no, or we can have some numerical labels that we can assign to the predicted output. So in the last class we have seen that if we have m number of inputs, okay, m number of inputs with m number of class levels, so x1 comma y1, x2 comma y2, so until we can have the last training examples xm comma ym. Okay, now this x1 is the data point or features, and y1 is the corresponding class level for this training example. So training example t1, training example t2, so until we can have training example tm. Okay, that means every training example we have the data point or feature point and the corresponding class level yi. Okay, so xi is the data point or feature point, or yi would be the corresponding class level. Okay, now considering these three problems, biometrics authentications, whether mail is spam or not, whether a tumor is malignant or not, so considering these problems we can have a binary classification. Okay, now to assign the class levels to the predicted output. So here the predicted output may be found as some continuous value. Okay, and we will make that continuous value to reach a binary decision by assign the labels 1 or 0 or yes or no. Okay, so therefore here if we have decided to assign the labels 0 or 1, okay, to the predicted output, then y belongs to 0 or 1. So in case of binary decision or binary classification, so for binary classification we can assign these class levels either 0 or 1. Okay, now for multi-class classification we can have more decisions beyond 0 and 1, so we can assign those uh, class levels. We can start from 0, then we can have 1, 2, or m number of class. So if there are m number of classes, then we can have m number of predicted value. That means for a particular individual or particular pattern or particular image, we can have only one predicted value, and according to the closeness of the predicted value, we can assign any level between 0 and m. Okay, so this is called the multi-class classification problem. Multi-class classification problem. Okay, so in binary class we have only two class levels, either 0 or 1. But in case of multi-class classification problem, we can have more than two classes. Okay, or more than two class levels. So according to the predicted value in the output, we can assign an appropriate class level as considering the closeness of the predicted value to the actual value. Okay, now let us consider if the predicted value is found to be close to the actual value, then we can assign 1. Okay, or if the predicted value is found to be far from the actual value, we will assign 0. Okay, now to make such decisions, we can define a threshold. So if threshold t is found to be 0.5, then we can have the decision like h theta x. So h theta x can be used in place of y approximated function y cap x. Okay, so this is equivalent to, so this h theta x. So this is very convenient to use this representation h theta x in place of y cap x. Okay, so both are equivalent. So if h theta x is found to be greater than equals to a threshold 0.5, then we can infer this decision by assigning 1 to the predicted value. That means the 1 becomes the class level, or if we have some decision like or the predicted value is found to be less than 0.5, then we can assign the class level 0. Okay, we can assign the class level 0. Now let us consider the problem of classifying tumors as malignant or benign. Okay, so suppose there are 4 data points or 4 training examples which are plotted over here. So this x-axis represent the tumor. Okay, and another 3 points, let us consider this point is plotted over here. So these three data points represent the another 3 training examples. So here we have plotted the 7 training examples. So x-axis represent the tumor and y-axis represent the class level. So we can have C in this case, or we can have h theta x. Okay, h theta x. Now in linear regression, what we need to find? We need to find the best fitting regression equation or regression line. Okay, so the best fitting regression line would be something like this, or we can have like this. Okay, now as I decided to have some threshold t equals to 0.5, so therefore we can assign the middle of this. So here the upper bound is 1 and lower bound is 0 over here, and this middle of this upper bound and lower bound would be 0.5. So this 0.5 is found to be the threshold. Okay, now what are the so here this is 1. Okay, now what are the training examples will be found to be malignant, and what are the training examples will be found to be benign? So to assign the label as malignant to the predicted value, so h theta, when the h theta x is found to be greater than equals to 5, then the training samples become malignant. Okay, training sample become malignant. Otherwise, when the h theta x is found to be less than 0.5, then the predicted value will become the benign. Predicted value will become the benign. So these two class levels are available with us. Now, as we have plotted these 7 training examples over here, so we need to predict which what are the training examples. So what are the different training examples that will have the malignant feature, and what are the other training examples that will have the benign feature. Okay, so as I represent the x-axis with tumor, and here y-axis is the predicted value. So now if we plot a point over here and try to estimate what are the different training examples will become the malignant, and what are the training examples will become the benign, then this will help us to estimate the predicted value. Okay, so here clearly we can see that when the threshold is decided to be 0 0.5, then these are the training examples which will be found to be as malignant, because uh, these training examples are found plotted beyond 0 0.5. Okay, so therefore this part, whatever the training examples which will be appeared beyond this point or beyond this threshold, so we can have those points or those training examples as malignant. That means those training examples will have the malignant nature, okay, or malignant feature, and the remaining training examples which will come under this area, okay, or less than, or the predicted value, when the predicted value will be found to be less than 0 0.5, then these are the training examples which will be found as benign nature. Okay,
Sir,
yes.
so that means, sir, we already know the predicted. I mean, sir, the threshold value of y-axis, and now we are when we have to predict, then we are finding out the threshold value of the x-axis.
No, we have decided that in binary, but in this particular binary classification problem, this threshold is already defined. Okay, so we will take this threshold to decide whether some training examples are found to be malignant or some training examples are found to be benign. Okay, that means some of the mails may be found to be spam, and some of the mails will be found to be non-spam. Okay, so for that we
Okay,
have
sir.
decided this threshold, and this is the upper bound. This is the upper bound. This is upper
Okay, sir.
bound is 1 and lower bound is 0.
Sir,
Okay.
sir, another, sir, you have drawn another threshold in sir, tumor axis, also vertical kind of threshold. What is? Can you
No, no.
explain?
This area, we can have this area would be 1.
Yes, sir.
So from 0 to 1,
Hmm.
this is 1. We can have
Hmm.
1. Okay.
Hmm.
And this is the upper bound of the x-axis. That means the tumor, whatever the, if we quantify the tumor with some numerical value, so that numerical value will be found between 0 and 1. Understood? If we quantify the
Yes, sir.
tumor
Yes, sir. Yes, sir.
with some numerical value or the real number, so the real number will lie between 0 and 1. Okay, and corresponding predicted value will also lie between this lower bound 0 and upper bound 1. Okay.
Okay, sir.
Okay.
So that means when we are predicting something,
Hmm.
some value, then we have to just check whether it is I mean lying above 0.5 threshold or below 0.5 threshold.
Yeah, yeah. So, depending upon the problem or the requirement of the problem, we can change the threshold.
The
Okay,
threshold
we
of
can change
hx.
the threshold.
The threshold of
So,
hx.
huh?
The threshold of h theta x.
Yeah, yeah, yeah. S theta x. So this predicted value, depending upon the predicted value or depending upon the requirement of the problem, we can always change this threshold. Okay, this threshold is not fixed. Now, this is what we are talking about, the linear regression. So in case of linear regression, we can have this best fitting line, regression line, and that will decide whether a tumor is found to be malignant or benign. Okay. Now suppose there are another training examples which is plotted over here. This is the another training examples. Now for this training examples, what would be the possible best fitting line? So if I draw that best fitting line, so suppose this is a new training examples, and for these training examples we have got this point. Okay, this point has been plotted over here. Now for this for adding these new examples, what so there will be a change of the base fitting line. That means the base fitting line will now found to be drawn as like this. Okay. Now in this case, what will happen? In this case, previously those examples which were assigned, which were labeled as malignant, now they will be found to be benign. Okay, because of this, because of adding these new examples, the training examples which were found as malignant, now they will be found as benign. Okay, and this example,
Sir.
yes.
Sir, what will be the logic if we try to implement the linear regression in the case of malignancy test?
No, in that case, there will be a large error.
Sir, what will be the significance of this straight line? If the point lies on the straight line, then it is malignant. It's like this.
No, 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 no. Because of this threshold, if we consider this threshold zero point 0.5, then because of this threshold, by adding this new example, okay, so the best fitting line is changed.
Yes, sir.
The place of this best fitting line is changed, and by changing this best fitting line, what we can see that earlier those examples were found as malignant. Now they will be found as benign, because the because this is the threshold point, and beyond this point on the right hand side we can have only one, maybe this example will come, and these examples will come. So this example and these two examples will be found as malignant, but earlier these two examples were found as malignant. Now after having the new best fitting line, these two examples will be now found as benign. Okay, so this is the problem of linear regression. So we cannot fit the linear regression line when we have such influential observation. So this point is known as influential observation. So having this point, the best fitting line will be changed, and when the best fitting line change its position, then position and orientation also, then having this best fitting line, earlier those points were assigned the level 1, now they will be assigned level 0.
Sir,
Yes.
sir, when we are trying to calculate the base fitting line, then sir there will be no threshold value of h theta x.
No, no, we are trying to introduce the logistic regression in terms of linear regression.
Yes, sir. Yes, sir.
So
So,
what are
sir,
the problems? What are the problems we can face in linear regression if we have such influential observation like this point? Okay, this is the influential observation. If we have such influential observation, this is the this is the this is the so this is the case of influential observation. If such
yes,
points
sir.
are there, or such points will be added after having a base fitting line, then because of this influential observation, the base fitting line will be changed its position.
Yes, sir. Yes, sir.
So
Yes, sir. Yes,
in terms of orientation, this base fitting line will change its position.
yes, sir.
And because of this effect, what will happen? Earlier, those points were found as malignant. Now they will be found as benign.
Yes, sir. Sir, I am. I got the point that for each point there may be a chance of the base fitting line can be changed. So, yes, I did. I can understand, but sir, want to I couldn't understand one thing, that sir, how when we have one base fitting point, how we are deciding which points are malignant, which points are benign?
Because of this threshold, we have already decided the threshold. Threshold would be 0.5, and based on this threshold, we can decide. That means the tumors which is less harmful, so
Yes, sir.
they have some quantified value. If we
Okay, sir.
decide if we decide to quantify a tumor with the help of some numerical values or real values, then if those real values are found below the 0.5, that means the those tumors are less harmful.
Sir, predicted value should be less than
Yeah, predicted value should be less than
less than
0.5,
0.5. Okay, sir.
so that we can assign those tumors as benign tumors. Otherwise, we need to assign those tumors as malignant tumors. Okay. Now, because of this influential observation or such influential observation, we can have the different base fitting line, and because of that base fitting line, we can have some unpredictable observation or unpredictable values. Okay. Now, what happens here, h theta x not always found to be less than 1 or less than equals to 1. Okay, and h theta x also not always found greater than 0. Okay, that means h theta x may be found as negative, okay, some negative value, or h theta x sometimes may be found as more than 1. Okay, now how to deal with this problem? So we cannot deal this problem with linear regression, because if we apply the linear regression, the error will be found to be very large. Okay, that means the residuals will be found to be very large, so we cannot apply the linear regression in this case. Now we can define a hypothesis representation. So we will call hypothesis representation. Now with hypothesis representation, we can bind this predicted value. But in case of linear regression, with this defined threshold, we cannot bind the predicted value between 0 and 1. Now we have to bind this predicted value between 0 and 1. Okay. So what h theta represent? H theta x. So we can write h theta x equals to theta tx, or more elaborately, if we write this representation, so theta t may be theta 0 plus theta 1 x plus theta 2 theta 1 x, theta 1 x1, theta 2 x2, and so on. So here x would be x1, x2. If we consider there are m number of points, so xm, and theta would be theta 0, theta 1, theta 2, until we can have theta m. Okay, so this theta is known as the model parameters, as I discussed in the last class, and here x1 to xm are data points, okay, or feature points. Now the combination of this theta t and x is the predicted value, so that we have to predict in the output. Now in the earlier examples, we can see that we cannot bind this predicted value which will lie between 0 and 1. Now we have to bind this predicted value. How we can do this? If we want to bind this predicted value, how we can do this? So for that, we will introduce a function which is called the logistic function. logistic function. Okay, or we can say this is sigmoid function. So interchangeably we can use this term. Either we can say logistic function or sigmoid function. Sigmoid function. Okay. Now with this logistic function or sigmoid function, we will bind the predicted value between 0 and 1. Okay. So if suppose the logistic function, so what we know about the logistic function is the logistic function gx is defined as 1 plus e to the power minus x. But in place of x, what we will write? We will write theta tx. So here we can have, so in place of x we will write theta tx. Okay, so the logistic function now will be defined over this combination of theta t and x. Okay, and we can have 1 divided by 1 plus e to the power minus theta t x. Okay, now this will give us the predicted value. So this may be equivalent to, we can say, theta h theta x. Okay, so this will, or we can have this, if we consider z equals to theta tx, then in place of g theta tx we can write g z. Okay, so g of z will give us 1 divided by 1 plus e to the power minus z. So in place of z we can write theta tx, the combination of model parameters and the feature points x. Okay, now this if I represent the predicted value in terms of the logistic function or sigmoid function, so we can bind the predicted value or the output value between 0 and 1. That means whatever the feature points or whatever the model parameters, so this, using this logistic function or sigmoid function, the predicted value will always come between 0 and 1. Okay. Now suppose the logistic function. So how the logistic function will look like? So this is the upper bound 1, this is the lower bound 0, and this is the threshold 0.5. Okay. Now the curve for logistic function, the sigmoid function will look like, so this is approaching to 1, so we can have like this. Okay. So this is the shape of the sigmoid function or logistic function. That means it will start from 0, then it will goes through the threshold 0.5 or goes through the point where we can decide the threshold, and it is asymptotic to 0, it is asymptotic to 1. That means it will approach to 1. So here, over here we can have the flattened curve. Okay, the curve becomes the flattened over here. So when it will be approaching to 1. Okay, so this is the limit of the upper bound. So this curve will approaching to 1. Okay, and on the negative side, this when the, so if we consider this is our z and this is our g of z. Okay, so in place of g of z, so g of z is found to be equivalent to h theta x, and z is found to be equivalent to theta tx. Okay, Now this curve will start from 0. It goes through the point where we can decide the threshold, and it will be approaching to 1. Okay, and at this place the curve is getting flattened. Okay, because this is approaching to 1. So at this, at after some point here we can have the curve getting flattened. Okay, now if we try to represent the hypothesis, so we can write h theta x. If h theta x found to be greater than equals to 0.5, then y becomes 1. Okay, this is the first assumption that we can make. And when h theta x will be found to be less than 0.5, y becomes 0. Okay, now why, how can we decide this? Suppose here we can have z theta equals to, if z theta is found to be greater than 0.5, when the z is found to be greater than, z is found to be greater than 0.5. Okay, that means from this observation we can decide h theta x will be found to be greater than 0.5 when theta t x is found to be greater than 0.5. Why? Because so the right side of this point lower bound 0, so we can have this 0.5, and left side of this lower bound 0 we can have the g of z less than 0.5. So above 0.5 or greater than equals to 0.5 will represent this area. That means the right side of this. Okay, and left side of this lower bound will be found as less than 0.5. Okay, now from the first observation, g of z greater than equals to 0.5 when z is found to be greater than 0.5. From this observation we can decide h theta x greater than equals to 0.5 where when theta t x is found to be greater than 0.5. And the second observation we can have g of z less than 0.5 when z is found to be less than 0.5. Okay, now from this observation we can have h theta x less than is found to be less than 0.5 when theta t x is found to be less than 0.5. Now from the first observation we can decide the class level to be 1, and from second observation we can decide the class level to be 0. Okay,
Sir,
yes,
so please point out where is the z equals to 0.5 in the curve.
yeah, this is the, let me show with another color so that you can understand this point. I am talking about this point
So this is the
because this
this is g
when
of
this,
z. Yes, this is g of z equals to 0.5.
yeah,
Sir, I am asking, sir, where is z equals to 0.5? Oh, this.
this point,
Okay, sir.
this point, this is 0.5. So this square area, so the h theta of x becomes 0.5 at the point which will lie on y-axis. Okay, and z becomes zero point 0.5 on at this point which will lie on x-axis. So this area is the square area, unit square area, or we can say this is the threshold area. Okay, and whatever the points beyond this area will be found to be as y equals to 1. Okay, y equals to 1. So whatever the observations or whatever the training examples which will be plotted which will be plotted inside this area will be found to be y equals to 0. Okay, otherwise if some points are found to be outside this area, then the class level become ones. That means the predicted value is found to be greater than equals to 0.5, because we have this curve was started from 0, and it goes through this point. Okay, and now it is approaching to 1, and after certain or we can say after a particular point, we can see that the curve is getting flattened. Okay, it basically tends to, we can say that g of z tends to 1 for getting the class level 1, and whenever g of z tends to infinity, the class level becomes 0. Okay, so this is the hypothesis representation. So this h theta x will be found to be greater than equals to 0.5. We will assign the class level 1, and when the h theta of x or the predicted value is found to be less than 0.5, then we will assign y equals to 0. Okay, so this is the hypothesis representation, and if this y is found to be 1, when this y is found to be 1, or when this y is found to be 0, so that can this hypothesis can also be represented with the probability, conditional probability. Okay, so if we write probability of y equals to 1 given x, which is parameterized with theta, model parameter theta, so this will give us the probability, so which infer the class level to be 1 or class level to be positive, or we can have probability of 0 given x parameterized by model parameter theta. Okay, now this will give us the probability 1, this will give us the probability 0. Now on the same observation, on the same training examples, for a particular pattern, we can have probability of y equals to 1 given x parameterized by model parameter theta plus probability of y equals to 0 given x parameterized by model parameter theta to be 1. So after adding this both this conditional probability, so we can have this 1. Okay, or either way, if we try to find the class level for the observations when the probability is found to be uh, 0, then we can rearrange this representation, and we can write probability of y equals to 0 given x parameterized by theta equals to 1 minus probability of y equals to 1 given x parameterized by model parameter theta. Okay, so in this way also represent the hypothesis. So hypothesis can be directly represented by this condition h theta, when the x theta is x is found to be greater than equals to 0.5, we can assign y equals to 1, or the class level would be 1, or in case of h theta x is found to be less than 0.5, we can assign y equals to 0. Or if we have these probability values on the given observation x with parameterized model parameterized theta value, then we can have this probability of y equals to 1 when given x, okay, plus probability of y given x would be 1. Okay, and from this representation we can decide, we can have the probability of 0 given x. So this becomes the 1 minus probability of y given x parameterized by model parameter theta. Okay, so in the next class we will be talking about the decision boundary and the cost function of logistic regression. Okay, the name of the logistic regression comes because of some historical reasons, because we are using the logistic function or the sigmoid function in the logistic regression model or a logistic regression function. So this logistic regression function is or logistic regression model is used to classify the objects or classify the patterns or classify some conditions. However, we are since classification is not classification model cannot be used for the regression. However, we are using the term regression because we are generating the continuous value as a predicted as the predicted value. Okay, so therefore when the continuous values are generated as predicted values, so we make that predicted value to infer some class levels. Okay, so after having the predicted value as continuous value, so we can decide about the class levels with that predicted value. Okay, so we are inferring some decisions about the class levels, and finally we get the class levels as binary decision. Okay, either we can have some positive class or either we will have some negative class. So accordingly we can assign the value uh, 1 to the positive class and 0 to the negative class. Okay, that's all for today. If you have any questions you can ask me, otherwise we will stop now.
Sir, slides.
Yeah, I will send you today. I will send
Sir,
this
sir, recordings.
recordings. Okay, so tomorrow I will upload all the recordings on Moodle platform. Okay, I will create a separate thread over there, then we will upload.
Sir, okay, sir. Can you sir, please share the link of the Moodle platform in the email?
No, you can access if you have login ID and password of Moodle, you
Okay, sir.
can access that lecture videos. Okay.
Okay, sir. Okay, sir.